Today's world runs on electronics. From our smartphones to our cars, tiny chips power everything. These chips are made using VLSI technology. VLSI stands for Very Large Scale Integration. It's a fancy way of saying we put millions or even billions of transistors on a tiny piece of silicon. These transistors are like tiny switches that control the flow of electricity. By arranging them in different ways, we can create complex circuits that perform amazing tasks. VLSI is important because it allows us to create smaller, faster, and more powerful electronic devices. Without VLSI, our smartphones would be the size of bricks, and our computers would fill entire rooms. VLSI technology is also crucial in applications like artificial intelligence, medical devices, and space exploration. Imagine you were building a house. You wouldn't just start building walls and rooms randomly, would you? You would first create a plan, or a blueprint, that shows where everything will go. Floor planning in VLSI design is similar to creating a blueprint for a chip. It involves deciding where to place different functional blocks on the chip. The goal of floor planning is to optimize the chip's performance, area, and power consumption. A good floor plan will minimize the distance between blocks that need to communicate frequently, reducing signal delay and power consumption. Additionally, it helps in managing heat dissipation and ensuring the chip's reliability. Once we have a floor plan, we need to place the individual transistors within each functional block. This step is called placement. It involves assigning specific locations on the chip to each transistor. Placement is crucial because it affects the chip's performance, power consumption, and manufacturability. A good placement will minimize wire length, reduce signal delay, and ensure that the chip can be manufactured reliably. The placement process involves complex algorithms to optimize these factors. Effective placement is key to achieving a high-performance, low-power, and manufacturable VLSI chip. Section 4. Connecting the dots. Routing. After placing the transistors, we need to connect them using metal wires. This step is called routing. It involves creating a network of wires that connect the different transistors according to the circuit design. Routing is significant because it affects the chip's performance, area, and power consumption. A good routing solution will minimize wire length, reduce signal delay, and avoid crosstalk between wires. Advanced routing techniques can significantly enhance chip performance by optimizing these factors. Section 5. Making chips work. It's all about the connections. Floor planning, placement, and routing are essential steps in VLSI design. They ensure that we can create chips that are small, fast, power-efficient, and reliable. These steps are all about making the right connections, ensuring that billions of transistors work together seamlessly to power our modern world. As technology advances, the importance of these connections will only grow, driving innovation in the semiconductor industry. Summary. Connections in VLSI design are crucial for creating efficient, reliable, and powerful chips. Future trends indicate that as technology progresses, the role of these connections will become even more significant, fostering further innovation in the semiconductor industry. In this chapter, we will explore the future trends in VLSI technology. As technology continues to advance, the demand for smaller, faster, and more power-efficient chips will only increase. Emerging technologies like quantum computing and neuromorphic computing are pushing the boundaries of what is possible with VLSI. These new paradigms require innovative approaches to floor planning, placement, and routing. GAP2S. For instance, quantum computing relies on qubits, which behave very differently from traditional transistors. Designing chips for quantum computers involves unique challenges and opportunities. Similarly, neuromorphic computing aims to mimic the human brain's structure and function, requiring a different approach to VLSI design. GAP2S. By staying at the forefront of these trends, VLSI designers can continue to drive innovation in the semiconductor industry, creating the next generation of powerful, efficient, and groundbreaking technologies. GAP2S. As we look ahead, it's clear that the future of VLSI is bright and full of potential. The journey of innovation is an ongoing one, and with each step forward, we get closer to unlocking the full capabilities of modern technology. Summary. The future of VLSI technology is being shaped by emerging fields like quantum and neuromorphic computing. These advancements demand new approaches to VLSI design, ensuring that the industry continues to innovate and create cutting-edge technologies. VLSI technology opens a world of possibilities. It powers AI accelerators, propelling AI computations, In healthcare, VLSI is revolutionary. It powers wearable health monitors and advanced imaging systems. In space, VLSI is essential. It enables satellites and rovers. VLSI drives innovation in AI, healthcare, and space exploration. It paves the way for a future full of possibilities. The story of VLSI technology is a tale of relentless innovation and progress. It all began in the 1960s with the first integrated circuits, marking a significant leap from individual transistors. This was the dawn of the microelectronics revolution. In this chapter, we will discuss the challenges and future directions in VLSI design. One of the primary challenges is managing the increasing complexity of chip designs. As the number of transistors on a chip continues to grow, so does the difficulty of ensuring that they all work together seamlessly. Advanced design automation tools and techniques are essential to manage this complexity. Gap 2S. Another challenge is dealing with the physical limitations of silicon. As transistors shrink to the nanometer scale, issues like leakage current and variability become more pronounced. Researchers are exploring new materials and device architectures to overcome these limitations. Gap 2S. Looking ahead, the future of VLSI design will likely involve a combination of traditional silicon-based approaches and emerging technologies. By embracing these innovations, VLSI designers can continue to push the boundaries of what is possible. Gap 2S. In summary, while the path forward is fraught with challenges, it is also ripe with opportunities. By tackling these hurdles head-on and adopting cutting-edge solutions, we can ensure that VLSI technology continues to evolve and drive progress in various fields. The journey of VLSI design is far from over, and its future holds exciting possibilities for all of us.